Hi, I'm Dr. John Chovic, and I'm the CTO of SwitchDoc Labs. And we're here today to talk about how to tune a lightning detector, how to tune an AS3935, which of course is the heart of the SwitchDoc Labs lightning detector, the ThunderBoard. So we're going to talk about how you tune a ThunderBoard and how to make it respond better to lightning strokes. So with that, let's get into it. Okay, what are we going to do today? Well, first of all, we're going to talk a little bit about how the AS3935 lightning detector actually works. Then we're going to talk about and understand each of the tunable parameters, even though we don't have to tune them all. We're going to understand the defaults, and we're going to understand the interactions between the various parameters. And finally, we're going to talk about a procedure to go through to tune your board. Most important part of that procedure is write down what you're doing and write down what the results are. This is complicated, or can be complicated, I should say, so you want to make sure you're following a methodical path through this tuning. So, starting off, let's flip back. Let's take a look at what the ThunderBoard is. Well, the chip right on the left-hand side, well, actually it's under the Grove I2C bubble there. That is actually the AS3935, the heart of the ThunderBoard, the lightning detector. We have three other interesting things on here: the Grove digital connector for the interrupts, and Grove I2C, which is used actually to talk back and forth to the chip. Remember, I2C is a bus that's used to communicate with a lot of sensors, and that's the interface we support on the ThunderBoard. Finally, there's one more thing we want to talk about, which is the interrupt active LED. It's actually the only LED on the ThunderBoard. When you turn the ThunderBoard on, when you apply power to the Grove I2C connector, you'll see the interrupt active light come on. That means that the ThunderBoard is there. It's raised an interrupt that you need to clear. Now, the deal about this is every single time the ThunderBoard generates an interrupt, whether it's a noise interrupt, a lightning interrupt, or a disturber interrupt, or a no interrupt, it will put that light on. When your software reads it, the light goes off. So you can always tell if that light is flickering, you're receiving interrupts and reading them. So that's a very useful little piece of information for you. Now, the AS3935 block diagram, this is pretty complicated. We're not going to go through it all, but I want to just talk a couple of things to you, a couple of things about this. First of all, let's take a look at the area up here. That is actually in the upper right-hand corner, is nothing more than the interface, the I2C, and also the optional SPI interface, which we don't support on the ThunderBoard. Okay, immediately below it is the most important block, and that's the AFE. It's the analog front end. Again, we're not going to talk too much about it, but here's the deal. You have a tuned oscillator right outside. That's our antenna. It has an inductor, a capacitor, and a resistor, and it's tuned to provide a bandwidth filter around 500 kilohertz, which is where lightning bolts actually make their characteristic frequency that the ThunderBoard picks up. It's not only the frequency, it's how it goes down and what it looks like coming in. So it's a rather complex detection algorithm. It's not just you get a spike of noise at 500 kilohertz and it's a lightning bolt. That's not the case. Okay, the analog front end takes that information in and it goes into two important blocks. The first block we'll talk about is immediately to the right of the AFE and down a little. It's called the WATCHDOG. The WATCHDOG actually counts the number of bursts that come in and looks at it, and as it gets some good bursts, it will send it over to the signal validation. Now, the signal validation block, which is in the lower right-hand corner, is what does all the fancy processing to determine whether an incoming signal is a lightning bolt or not. It takes a lot of power, so it's mostly shut off. It's only when the WATCHDOG says, hey, I've got an interesting pulse here for you to look at. Plus, there's one more thing that's very important and the most tunable parameter of the entire chip. That's those two blocks immediately above the signal validation block, kind of in the upper right-hand corner of the diagram, where it says noise flow level generation and noise floor execution. It's looking at the noise floor. So you have two things. You have a threshold you set for noise. And if the noise gets above that level, then the chip says, well, this isn't a lightning bolt. It's too noisy of an environment. I'm not going to run the signal validation. And that noise floor is the critical parameter to set, the most important parameter of all the parameters to set. The signal validation, if both of these things say, yeah, this looks like a pretty good thing, then the signal validation happens. It does energy calculations. It looks at the waveform itself and makes sure that it is a lightning bolt, very likely a lightning bolt, and then generates the appropriate interrupt saying it's a lightning bolt. The noise floor, if you exceed the noise floor, that also generates an interrupt. And then there's one more thing that generates interrupts, and they're called disturbers. Now, a disturber is a man-made signal that looks like lightning but isn't lightning. It doesn't have the right spectral and time domain characteristics. So we'll talk more about disturbers in the following slides. So let's see what the tunable parameters are. The most important ones: noise floor, indoor-outdoor selection, which actually affects the noise floor primarily, and finally disturber detection. Those three parameters are the most important ones. Disturber detection is probably the least important of these three, but we'll go through them all anyway. Then the less important ones are spike rejection, the watchdog threshold, and when I say less important, is the system is less sensitive to them, but they still can do some interesting things. Finally, the tuning capacitor, which is how we can tune our oscillator to be right where it should be, about 500 kilohertz, regardless of the outside components, which will tend to vary a little bit. We'll talk about that. ThunderBoards come with a pretty well-tuned system. The default values are pretty good for our devices, but we'll talk about later how you can actually verify what the tuning capacitor should be and put your own value in that. Okay. We use this product, we use the ThunderBoard in a number of our different weather products, OURWEATHER and GroveWeather Pi. Now, from the OURWEATHER page, you can see these parameters, the administrative page. You can see these parameters in the lower block. You can see the noise floor, tuning capacitor, watchdog threshold, and spike rejection. And that's how you'd program them on OURWEATHER. In GroveWeather Pi, you actually set them programmatically in the Python for GroveWeather Pi. We may change that in the future, but right now that's how you do it. Okay, revisiting the tunable parameters before we get them in again, I'm adding one more thing right in the middle. That's somewhat important. You know, testing a lightning detector is a difficult thing to do unless you have lightning storms all the time. Well, one thing you can do to make that testing process easier is we sell a ThunderBoard lightning simulator that actually simulates the spectral content that the ThunderBoard is looking for lightning, so you can actually test it more easily. However, you know, that's an optional thing. If you get your ThunderBoard responding to noise inputs by setting the noise threshold really, really low and you have noise around, well, then you know the ThunderBoard is working because you're getting interrupts. By changing that noise threshold so you don't get, you're probably working. But if you want to test it, you're going to have a lightning simulator. So let's now talk about the most important parameter. What is the most important parameter? The noise floor. Now, what we're actually doing here is setting the noise floor threshold. It's when the actual noise level is below the noise level threshold, then the system, you might get lightning bolts coming up here, and it will try to decode them, try to determine whether the lightning bolts or not. However, if the noise level comes up, well, then when the noise gets above the noise threshold, then it generates an interrupt saying, hey, the ThunderBoard is experiencing too much noise and is not detecting lightning. And that's what we call the int-n interrupt, of which the software that comes with the ThunderBoard, as well as GroveWeather Pi, as well as OURWEATHER, will all report this in various different ways. So, now, changing the threshold, having this noise threshold also rejects disturbers, which are man-made spikes of electrical noise that might be in the same frequency range as lightning, but doesn't look like the lightning range. So these things are all kind of tied together. But the noise threshold is the most important parameter. Now, what does this mean really? Higher noise floors, higher numbers for noisy environments, lower for quiet environments. Lower numbers reduce the sensitivity to as small amounts of noise can generate the noise floor interrupt. So, it's a trade-off. The default is 2, the range is 0 to 7. We usually run it around 2 or 3, providing we've moved it away from the noise. That's what we'll talk about in a moment. Now, looking at the chart from the specification here, basically we don't have to worry about what these numbers really are. We just have to realize what difference they are. For example, if we look at the continuous input noise level here, at the lowest noise threshold value, when it's set for the outdoors, it varies from 390 to 2000. That's about an 7 to 1 difference. So there's a large level of threshold adjustment you can do. We'll come back and take a look at the second column in just a moment. So, if you have lots of noise, use higher numbers for noisy environments and lower numbers for quiet environments. But let's talk about what generates that noise and what causes problems for your ThunderBoard. Well, cell phones, monitors, big computers, your Raspberry Pi, your Arduino, close radio stations, electrical motors, 3D printers, etc., all these things make noise. Cell phones and monitors are two things we often place our development systems near. So you got to remember that. You got to think about that. Now, the noise created by these units will affect the detection of, obviously, of lightning and will increase the noise threshold. So if you have a 50-centimeter cable, it's a good thing to put your ThunderBoard as far away from your Raspberry Pi as is reasonable. It's also good to move it away from monitors, not have your cell phone sitting next to it. And so there's all these things that affect electrical noise. People with drills, even a couple of doors down, really, all sorts of things like this. Your washing machine turning on, all these sorts of things can create noise. And our system is designed to filter out as many of these as possible. But it's the ongoing noise threshold that you need to be most concerned about. So, we've got software. Why don't we automatically adjust this number on the fact we're getting noise interrupts? You get a noise interrupt, well, you crank the threshold up higher until you stop getting them. Well, the reason why we don't do this is because if things are noisy, it just ratchets up. It's much better, we feel, to experiment and find the right number. But, of course, you can go in and put that in the code anytime because we supply you the code. Now, things are noisy, it ratchets up. The higher noise thresholds reduce sensitivity to lightning. Because you think about it, well, these spikes don't go in there. If you have real low levels, it's all tied in to sensitivity all through that. Okay, now, the indoor versus the outdoor switch that you have. It's either a 1 or a 0. Now, here's what it does. It changes the input noise thresholds from the first column to the second column. And you can see there's a 10 to 1 difference. Almost a 10 to 1, almost 20 to 1, 15 to 1 difference between these two. So if you set it on indoor, that means you have a very low threshold, and which means any kind of noise is going to bump above it. Or any, like sitting next to your monitor or something, will bump above it. So that's the thing to consider. Now, the whole thought about this is if you have it outdoors, there's not, it can be less sensitive because the lightning bolts are stronger. If it's indoor, you have multiple things coming in, attenuating the walls, metal in your walls, all sorts of things like that, that attenuate the electrical fields generated by the lightning stroke. And that's the rationale between indoor and outdoor. What you're going to find is this is mostly set by the kind of noise you have in your system. Setting it at an outdoor level will generally do the best job, even if you're indoors, providing you have electrical noise. If you don't have a lot of electrical noise around, then set the thresholds down. The key is you can experiment with all this stuff, get the values, write it down so you know what your test conditions were. Okay, now that's not that complex for setting the noise level. You bump the noise level threshold up until you don't get noise interrupts anymore. So there you've got it pretty well set. But remember, that reduces the sensitivity. Okay, so man-made noise is often stronger indoors than you think, like we talked about. with the various motors in your office, the monitors, the computers, your Raspberry Pi. So you need to think higher noise thresholds sometimes, indoors than outdoors. Welcome to the world of lightning detection. Now, we had mentioned disturbers just a little earlier in this talk, and if you have a signal that goes above the current noise threshold that you've set with the noise floor, and then we check it out for lightning. If it doesn't fit the lightning profile, which is this time domain thing going across here, as well as frequencies, then it says, this is a disturber, and we'll generate a disturber input. Remember, disturbers are man-made noise sources. You can think of the noise floor as continuous noise, and a disturber a man-made non-lightning spike signal, like turning on a drill right next to it or something. So if you're getting a lot of disturber interrupts, you can turn it off with this parameter. All this does is switch off the reporting of disturbers. It's nice to know whether you're getting a lot of disturbers when you're setting up your system. It's really quite handy. But once you've got it all configured and whatnot, you just don't need this stuff. The various Raspberry Pi IoT devices and the Arduino-based IoT lightning detector devices we sell both report this as an N or a D on the screens. Now, let's move along to spike detection. Notice we're getting to the less important things that you can set. Now, this parameter changes the way the chip will reject input signals, impulse signals that look like spikes. These are related to disturbers. They're kind of the same thing. Higher values improves the disturber rejection with a decrease of lightning detection efficiency. So, you can get rid of the noise, but you reduce your sensitivity to lightning, which means you may not detect lightning bolts out at 37 kilometers, maybe it's only 20 kilometers or something like that. It's all a trade-off. Default of 2, range of 0 to 7 for this. Now the watchdog threshold, we defaulted to 1. The input, as we talked about, the analog front end on the block diagram enables the signal validation when the input signal goes over a threshold. If the validation will be stopped if it's classified as a disturber, a man-made noise, or it will continue on for validation to see if it really is a lightning bolt. Remember that the watchdog threshold being higher reduces the sensitivity of the lightning detector. That's a big effect on sensitivity, and we even have a graph to show you. You can see here that the low levels in the watchdog timer will bring us up detection efficiency around 50%. It cuts it down when we're up to about 10 out of 16, out of 15. When we get it down to 10, it's down to about 30%. That's not very good. It's a huge, or it's 20%. It goes from 40% to 20%. Furthermore, the higher the number of watchdog value, the less distance you get, which of course is related to sensitivity. The last parameter, the tuning capacitor. Okay, this adjusts for variations of the external components that form that little oscillator outside that's tuned as a bandwidth filter is tuned at around 500 kilohertz. This will generate from 0 to 120 picofarads in steps of 8 picofarads. Whoa, that was a gobbledygook sentence. Basically, you add little caps onto it to make it so it'll be right at 500 kilohertz. The default is 0, but we set the ThunderBoard to 2 because of the history of the components we've been using in these devices. The range is from 0 to 15. Now, there's no real way of tuning this with a Raspberry Pi because the operating system gets in the way. But if you have an Arduino running around and running our demo software for the Arduino, then you can find out the exact value for your board and your chip. And that's pretty cool. You can do that. The software, the Arduino drivers that we provide for the As3935 will actually, the ThunderBoard will actually give you the actual value to make it perfect. If it's off a little, it reduces the sensitivity. But I have to tell you, this will probably work just the way it is out of the box. But if you're having a problem, especially with noise, you have to go in and fiddle with these parameters. So again, what are the steps to tune the ThunderBoard? Well, you set all the values to default. You optionally tune it with an Arduino to get that tuning capacitor value. Run the software, see what it does. If you have the simulator, run lightning bolts. See if you're receiving lightning bolts. Remember, a lightning simulator has to be pretty close to the Arduino board because of the power involved there. You want to move the system away from noise sources. Don't use short little Grove cables for your lightning detector. Put it away 50 centimeters. Remember, the noise created from a Raspberry Pi goes down with the square of the distance from it. It's a square law. So if it's twice as far, it's 4 times less noisy. So those are important things to remember. Run tests, set the noise threshold to where you don't get that interrupt noise anymore. Run tests with indoor and outdoor, but write your results down so you know what you're doing. And finally, once you have all these optimized, play with some of the other tuning variables to see what it is. Turn off your disturber inputs when you're comfortable with things, and then you're ready to detect some lightning. So, let's just summarize here. Okay, what are the most important parameters? The noise floor. Second most is indoor-outdoor detection. Finally, indoor-outdoor selection, I should say. And finally, the disturber detection. The less important are the spike threshold, watchdog threshold, and the tuning capacitor. Experiment mostly with the noise floor to get your system so it operates in the noise environment you're in. You know, all sorts of stuff creates electrical noise. And we can't hear it, we can't feel it, but it's there. And a device as sensitive as a lightning detector can pick this up. And that's why all the effort on bringing the noise floor to the right things. Finally, keep track of experiments and results. Now, take that ThunderBoard out there and let's detect some lightning.